Okay, so let's get started properly. What I'd like to talk about is processes in protoplanetary disks, and I'd like to begin with some just motivation of the topics that we're going to try and cover during my lectures during this week. So part of this course is going to be about observations, of course, and I think one of the exciting things about protoplanetary disks, one of the really revolutionary things in recent years, has been the tremendous amount of direct observations we can make of those systems. And if you go back and you look at those old Saas-Fee proceedings from even just 10 or 15 years ago, one of the very striking things you'll discover is the amount of direct observations we have now that we didn't have really in the relatively recent past. So we have now a tremendous amount of information of observations of protoplanetary disks, and we can observe a whole different range of properties of disks in different wavebands and with different instruments. So we'll certainly hear a lot about dust observations. So this is an image that I'm sure we'll be seeing more of HL Tau with ALMA, just released last year. And these are dust observations that are probing a range of size scales, not just with ALMA, but also with infrared instruments and so forth. The range may be from micron sizes of dust up to millimeter scales within disks. Now we can also observe the gas. And in the gas, we have the advantage of not only being able to observe the emission, but we can also say something about the kinematics of gas within the disk. So here's some images by Rosenfeld et al., protoplanetary disk, here color-coded with the Doppler shift measured in molecular line traces. So in general, it's quite hard to observe the hydrogen in these disks, as I'm sure we'll hear about, but we can observe CO and many other molecules in some cases within these disks, get information not just about the chemistry, but also about the kinematics of those structures. So these are observations of the structure of disks. We also have observations about the evolution of disks, and these I might divide into two categories. We have some observations that really tell us something directly about the time dependence of these systems. So here's one example from old work now by Hartman and Kenyon. This is a light curve of a so-called F Uranus object. This is 50 years of observations. This is the visual magnitude of these systems. Here this system showed a large outburst and then remained in a high state for now many decades. So in some cases we have really direct information about how these systems are evolving on timescales of sometimes decades or even approaching centuries. For much longer timescales, we have only indirect observations from looking at the population of disks and how those evolve with time. Here's an example of that. This is Hernandez et al. This is the disk frequency as a function of age in many young clusters, showing this characteristic decline. Almost all disks, almost all stars in young clusters have disks. By the time we get to ages of 10 or 20 million years, the disk fraction is rather low. So we have evolution here from population studies telling us something about, on the average, how disks evolve over time. So we have a lot of data to constrain theories. Now, what do we hope to learn from those observations? Well, there's a long list of things we, of course, would hope to discover from analyzing those observations. If we just think about the disks themselves, we can see that the disks are evolving. So why are those disks evolving, and what are the physical mechanisms that are responsible for that evolution? What are the conditions like within the disks? If we're interested in planet formation, we may be interested in many different aspects of that problem. What is the temperature in the disks? What is the density? What is the ionization fraction? How turbulent the disks are? These are all topics which we will be discussing during this week. And then, moving sort of more directly towards planet formation, how do the solids that we know are present within the disk interact with the gas and with themselves, eventually to grow into larger bodies in the early stages of planet formation? Going on, we have questions about what sort of structures do we have in disks. And one of the things I'm going to be discussing in my lectures here is questions of how we might produce structure within disks, either with planets or without planets. So over here, you have some images of the transitional disk, IRS 48. These are ALMA observations showing that the dust in this disk is extremely lopsided. It's almost all on one side of the star. On the other side of the star, there's almost no emission. So clearly disks, even though maybe on the average they are axisymmetric structures, they're not completely axisymmetric. In some cases, in fact, observationally, they're very non-axisymmetric. So when we see these kind of structures, does that immediately imply that there are planets formed within these disks, or are there other mechanisms that could produce structure within disks, even if we don't have planets? When we do have planets, though, how do those planets interact with the gas disk? Does it produce this kind of asymmetry? What other kinds of structures can we produce? So the goal of this part of the course is really to introduce the disk physics that in some way links the observations to these questions of planet formation that we're interested in. So we're going to have separate lectures on the observations and on many of the planet formation processes themselves. So I consider this middle section, if you like, to be the sort of glue between those two parts of the course. So this is the outline of what I'll be discussing in my 8 lectures this week. I'm going to begin today by talking about disk structure and disk evolution. And so we're going to start with really quite basic a discussion of what we know about the structure of disks, the equilibrium structure of the disks, and simple theoretical models for how those disks evolve. We'll then go on and talk about the possible mechanisms that lead to disk evolution. One of the important ones is turbulence, which is also something that we're directly interested in from the point of view of planet formation. We'll then discuss something about episodic accretion. So going back to that light curve I was showing of an F-Uranus object, we see that there are some very dramatic outbursts of accretion in young stellar objects. What do we understand theoretically about what might be driving that kind of evolution, and what kind of role might it have in different stages of the planet formation process? So these first 4 lectures are all going to be concerned primarily with evolution, or the structure and evolution of the gas within disks, which by mass is the majority of the material that we have there orbiting the star. Then later we'll be discussing, instead focusing more on the solid component of disks and how that evolves and how that interacts with the gas. So we'll say something about how individual particles, small solid particles for the most part, would interact with the gas. As we'll see, those can interact with the gas quite strongly and therefore have a very different evolution from that of the gaseous component. And then we'll discuss something about how we might form structure within disks. And those lectures 6 and 7 will be somewhat mixed up. We're really just interested in how we form structure, and we'll sort of distinguish somewhat between a permanent structure that might be present in disks at places such as the snow line, and then transient structures that maybe might form out of the turbulence within disks and perhaps be important for concentrating particles. So we'll discuss there a variety of ways in which structure might form and what we might know about that from looking at observations. And then finally, we'll discuss the end of the story, what gets rid of disks at the end of the disk lifetime, photoevaporation and any alternatives to photoevaporation that might remove the gas from the disk. So there's going to be a mix of topics here and also a mix of levels. I know there's a range of backgrounds here in the class this week. So my goal is to both say something about the most sort of elementary theoretical concepts, but then also to show some very recent results, particularly on some of the more advanced topics we have later in the week, and also try to highlight perhaps places where I think there are still things, basic things, left to be discovered. Let me emphasize then on that note that this is still a new subject. There's still a lot to be learned about protoplanetary disks, about planet formation, what's going on within these disks. So for sure, some of the things I will say this week, perhaps some of the things the other lecturers will say as well, will be unintentionally wrong. Unfortunately, we don't know which those things are, but I'd very much encourage you to ask questions, to talk among yourselves, to ask about how we could do better in calculating or observing the different things that we're talking about this week. Okay, so let's begin by thinking something about disk structure. And the basic principles of disk structure are derived from the fact that observationally we know that disks, protoplanetary disks, are very long-lived structures. So if we think about disks in the context of star formation, there are issues in the star formation phase about how you form the disk and avoid the disk actually accreting very rapidly onto the star during the very earliest, maybe 100,000 years of the star formation process. And that's sometimes described as the magnetic braking problem of star formation. If stars and disks form threaded by magnetic fields, it's possible for those magnetic fields to remove a lot of the angular momentum from the disk and lead to very rapid accretion of the gas onto the star, preventing you ever having a long-lived disk in the first place. Now, we won't be saying anything about that star formation aspect really during this course. So we're going to be thinking about the systems that are observed, which typically live for several million years. So even at the outer edges of those disks, maybe at 100 AU, where the orbital period is 1,000 years or several thousand years, those disks are living for many thousands of dynamical times. And in the inner regions, the terrestrial planet-forming regions, of course, the disks are living for millions of dynamical times. So disks are very long-lived structures, and therefore they can generally be well approximated as being quasi-equilibrium structures that evolve rather slowly over the time. So their basic structure then is set by hydrostatic equilibrium, balance between gas pressure and gravity, assisted by rotation if we're thinking about the radial direction, thermal equilibrium, and local ionization equilibrium. And in most places, most parts of the disks, these are going to be good approximations for describing their structure. Now, we should say, of course, that there are some aspects of disk structure which are not described well by equilibrium conditions. In particular, if we're interested in disk chemistry, particularly in the outer regions of disks, where the temperature is very cold and the density is rather low, it may take a very long time for chemical reactions to come into equilibrium. So if we're thinking about what's going on at 100 AU in a protoplanetary disk, and we're interested in different chemical reactions that might change the chemical abundance in that region, we have to think very carefully about whether those reactions will have had time to reach an equilibrium situation or not. Often, they will not have had time to reach equilibrium. So if we start thinking about hydrostatic equilibrium and the disk structure that's implied by that, let's begin by just thinking of the very simplest sort of disk model we could imagine. Let's think of a disk whose thermal balance is set by heating from the star. So the heating is primarily coming from stellar irradiation, illuminating the upper and lower surfaces of the disk. The pressure is provided by gas pressure, and the disk itself is of low mass compared to that of the star. And these are approximations that are not always met in protoplanetary disks, but there's a wide class of disks, perhaps particularly late disks, perhaps the disk we're most interested in from the point of view of planet formation, where these are very good assumptions for what's going on in the disk. So if we have such a system, the disk is heated from the star, so the heating is primarily on the upper and lower surfaces of the disk, and so when the disk comes to thermal equilibrium, as a first approximation, we might assume that it was vertically isothermal. So being heated from the top and bottom surfaces, so the inner parts will come to thermal equilibrium that will be vertically isothermal. So if we have that situation, here's the midplane of the disk, and we're imagining some distance above the disk, some height z above the midplane. Then we have a balance here between gravitational force. Most of the gravitational force will be towards the star, but there will be a component of that gravitational force down towards the midplane, and that unbalanced gravitational force will be balanced by a pressure gradient reflecting the fact that the disk is dense near the midplane and is of lower density as we move away from the plane. So if we consider the hydrostatic equilibrium equation, Gz here would be the vertical component of gravity. That would just be given by the gravitational force times sine theta, where theta is this opening angle to the point in the disk we're considering. If we then assume that the disk is isothermal, we could write the pressure as rho times the sound speed squared, where rho is just the density. And moreover, if we assume that the disk is rather thin vertically, so z here is much smaller than the distance away from the star, then this gm star over d squared sine theta, we could say, well, sine theta is just z over r, and d squared here, d and r, if this angle theta is small, are going to be almost equivalent quantities. So in total then, this gravitational force will be gm star over r cubed times z, and this here is just the square of the Keplerian angular velocity with which the material is orbiting about the star. So if we take those expressions, we have a very simple differential equation which we can solve here to get the vertical density profile, which will be a Gaussian with a disk scale height h, which is the sound speed divided by the Keplerian angular velocity. So this is sort of the basic assumption we often make in modeling disks. In the simplest case, where the disk is irradiated by the star, therefore it's vertically isothermal, It has only weak self-gravity, so the gravity is predominantly that from the central star. We end up with a Gaussian vertical density profile, a very steep fall-off in the density as we move away from the midplane, much steeper than we would have, say, in a planetary atmosphere, where characteristically we would have an exponential decline of the density with height. We can then continue with some more definitions. We define the disk surface density sigma as being the vertical integral of this density. And so if we have this Gaussian profile, there's then a simple relationship between the midplane density, the surface density, and this Gaussian scale height h there. So we can take those expressions and then ask, what are the sort of basic physical conditions we expect to be present in protoplanetary disks at different scales? So let's imagine we're at 1 AU, 1 astronomical unit. We have a surface density of 1,000 grams per square centimeter, which is not an unreasonable value, perhaps, for the surface density at those radii, and that this thickness divided by the distance from the star, so this geometric thickness, h over r, is about 0.03. And again, that's a fairly reasonable value for models of protoplanetary disks. Well, if we plug those numbers in, what we get is that the midplane density is something like 10 to the minus 9 grams per cubic centimeter, and the sound speed is something like 1 kilometer per second at that location in the disk. Now we can combine those numbers and ask, well, what's the mean free path in the gas? Take a gas molecule, how far will it travel before it typically collides with another gas molecule in the disk? And the answer we get there is that that mean free path is of the order of centimeters. Okay. So these are numbers that will be important for some other purposes in this course, particularly when we start thinking about solid evolution in the disks. And the main point I want to emphasize is that even though we imagine protoplanetary disks as being very dense structures, and certainly by comparison with molecular clouds or many other astronomical structures, the gas in protoplanetary disks is very dense. In a sort of more absolute sense, of course, the density is still very low. 10 to the minus 9 grams per cubic centimeter is a tiny density, and a mean free path of centimeters means that many particles we're interested in, certainly if we think about dust or millimeter-sized particles in protoplanetary disks, the sizes of those particles will actually be smaller than the mean free path of the gas in the fluid. So when we think about millimeter particles, which are things, of course, we directly observe in protoplanetary disks, those are particles that do not experience the gas as a fluid because the gas has a mean free path that is larger than those size scales. And that will be important when we think about how the gas evolves in the disk and how it interacts with the solids. Okay, so those are sort of the standard assumptions for what the vertical density profile in the disk could be. Are there any places where this might be wrong? What might alter the vertical density profile and give us something different from that simple Gaussian profile? Well, one thing that could clearly alter the vertical profile would be self-gravity. If the disk is sufficiently massive, then the dominant component to gravity will not be the acceleration due to the star, but will instead be the acceleration caused by the sheet, the slab of gas itself. So I'm not going to derive this. This will be one of the things that will be in the notes. But the condition for that is roughly that the disk mass divided by the stellar mass be larger than this ratio h over r. So for a disk where h over r is maybe 0.03 or 0.05, disk masses that are 10% would certainly be large enough that disk self-gravity would be very important for the vertical structure. If the disk mass is instead 0.1% of the central star mass, then it's quite fine to ignore self-gravity for the purpose of computing the vertical structure. And later we'll be talking about other aspects of self-gravity, and it turns out this same condition, basically that the fractional disk mass exceeds the disk thickness, is also the condition for generating non-axisymmetric structure, spiral arms and structures of that kind within the disk. So when self-gravity sets in, basically it sets in not just for the vertical structure, but also for the non-axisymmetric departures in the disk itself. Now the other thing that might matter is magnetic pressure. So we don't know very directly how strong magnetic fields are within the gas, within protoplanetary disks. And if those magnetic fields are strong enough, they could contribute to or potentially even dominate the thermal pressure in setting the vertical structure. And there's some evidence that this may be the case. So here's a plot from work by Hirose and Turner from a few years ago. This is log density as a function of height. And what you see here plotted as this first dashed line would be that Gaussian density profile you would expect if gas pressure alone was dominating the vertical structure of the disk. And what Hirose and Turner found was that that's a very good approximation close to the midplane of the disk. These are calculations at 1 AU, so this would be here within about the first tenth of the distance above the disk. But then as you go further up, there's a flattening of the density profile, which starts to approach instead an exponential form at large distances above the disk. And this is due here to magnetic fields within the disk that produce a magnetic pressure. They produce, if you like, a disk corona analogous to the solar corona that eventually dominates the vertical structure of the disk. And in these simulations, they found this transition from a gas pressure-dominated core to a magnetically dominated atmosphere occurred at a height of about 4 scale heights above the midplane. So that's well above where most of the gas in the disk is, but nonetheless, these are scales where many observational probes that are really probing the skin of the protoplanetary disk might be quite sensitive to. So if we're really interested in the surface layers of the disk, we may be above the region where gas pressure is dominating, and we may have to worry instead about magnetic pressure. Now, something else I'll mention, and we'll say more about tomorrow, is that the strength of these magnetic fields that lead to this exponential tail depends on the magnetohydrodynamic processes, the MHD processes, that are present within the disk. And as we'll see, there's some very recent simulations just from the last year or two suggesting, in fact, that this work from a few years back may have underestimated the strength of magnetic fields, particularly in the terrestrial planet-forming region. So there could be stronger magnetic fields, and therefore a larger departure from this Gaussian density profile in that region. So the message here, perhaps, is that if we're interested in observations of disks and trying to infer something from observations of disks, we should certainly think that the Gaussian profile is, if you like, the nominal profile we have for the disks, but we should also be looking for places where maybe there's evidence for something different, because at least from a theoretical point of view, that remains quite possible. Okay, so that's the vertical structure. What about the radial structure? Well, we can't use a similar argument to predict the radial run of the surface density or the midplane density within the disk, because in the radial direction, the gravitational force from the star is predominantly just balanced by rotation. Okay, so we can't come up with, if you like, a hydrostatic argument for saying how the density runs with radius. What we can look at is what the velocity profile ought to be within the disk. And the general picture here is that if we consider gas at some distance from the star, the dominant balance is between gravity and rotation, but then there's a small component which is due to a pressure gradient. And in most cases, at least in the mean, we expect the disk to be hotter and denser close to the star, so the pressure in the disk will be larger at small scales, and it will decline as we move further outwards. So the pressure gradient will be pointing outwards, it will be opposing gravity and working with the rotation to give us equilibrium in the disk. Now, if we consider that the disk is slowly evolving and is axisymmetric, then the momentum equation, which would look like this, the other terms to that involving viscosity, magnetic fields, and so forth, which we're going to ignore, the momentum equation would say that the acceleration here on the left-hand side is balanced by a pressure gradient and the gradient of the gravitational potential phi. Now, if we imagine that the disk is slowly evolving, we could say that this dv dt here, we can ignore that term. And so what we end up with for an equilibrium condition is just a very simple one, that v phi squared over r, so this would be the azimuthal velocity of the gas in the disk, has two components. It has a gravitational component, just the gravitational force, and then a pressure gradient, which will depend on how the pressure, let's say in the midplane initially, varies as we move away from the star. Now, we can look at this just from a dimensional point of view and say that the pressure, we said, is the density times the sound speed squared, and the sound speed scales with the thickness, the geometric thickness of the disk h, vertical Gaussian scale height. So this second term on the right-hand side of this force balance equation is order h over r squared compared to this first term, which is just the dominant balance of gravitational and centrifugal force. So we can do a specific example of that. Let's imagine we have a surface density that scales as 1 over the distance from the star, and a central temperature that goes as r to the minus 1/2. So those are fairly typical scalings that are often assumed for many protoplanetary disks. Well, in that case, the gas azimuthal velocity is just the Keplerian angular velocity, the Keplerian velocity, so the velocity that a point particle would have orbiting the star on a circular orbit, multiplied by this correction factor, which is indeed second order in this ratio h over r, the geometric thickness of the disk. So we can take some numbers there. Let's go back to 1AU and make this same assumption about the disk thickness. Well, this second term here then works out to be very small. Okay? The gas is sub-Keplerian. It's going slower than the Keplerian speed because of the radial pressure support by about 1/4 of 1%. Okay? So if you like, for a first approximation, that is a completely negligible term. However, we could also ask just what is that difference in absolute units? What is the difference between the gas speed affected by the pressure gradient and the Keplerian speed if that pressure gradient was not there? And with these same parameters, that number works out to be about 70 meters per second. Okay? Now, 70 meters per second is not, in an absolute terms, a small velocity, right? 70 meters per second is hopefully faster than you're driving on the motorway or the freeway, unless you're likely to be stopped by the police. So the gas is sub-Keplerian by a very small amount. So if we're just interested in gas dynamical processes, we can basically ignore this 1/4 of 1%. So if we have non-self-gravitating disks, we don't have to worry about any other potential contributions. Those can be treated as Keplerian really for all practical purposes. When this afternoon we talk about disk evolution, we'll make that assumption. We'll just completely forget this radial pressure gradient. However, this small deviation has a very large importance, an outsized importance, for particle dynamics. And we'll also talk about that, and I think Willie will also talk about that quite extensively in his lectures, when we start thinking about particles anywhere from maybe millimeter-sized particles up to objects that would be hundreds of meters in size. There we're thinking about aerodynamic effects of those particles on the gas, and this 70 meters per second turns out to be a critical number in how those particles evolve within the gas disk. Now, we can also ask how things vary vertically, and that is something else we can work out fairly straightforwardly. If you take a gas disk with some specified radial density profile and an isothermal vertical profile, you can calculate the equilibrium structure that you would expect and how the rotation should vary going from the midplane towards higher scales within the disk. And at that same order of h over r squared, there are deviations, there is shear in the velocity in the disk with height above the midplane. And here's just a couple of illustrations of that. So this is the deviation from the midplane Keplerian velocity in units scaled with r over h squared as a function of height. Here's the gas rotation. It's sub-Keplerian near the midplane. As you go higher away from the midplane, there's a same order variation in the velocity as we go vertically. So although roughly speaking, the gas at each radius rotates at the same speed around the star, at the next order of approximation, there is actually some vertical shear in the velocity field with height. Likewise, if you took a small particle that was on a Keplerian orbit at that particular height and asked how fast that would rotate relative to the local gas, that function also has a variation of the same order of magnitude as you go away from the midplane. So these are calculations by Takuchi and Lin. Something that's interesting recently is that effects of this order are now potentially observable from kinematics of molecular lines. So even though these are small effects, much smaller than the orbital speed of the gas around the star, they are within reach of being seen, for example, with analysis of ALMA observations. And these were discussed, for example, in fairly recent work by Rosenfeld et al., analyzing particular protoplanetary disk kinematics. Now, are there more dramatic things? Well, there certainly could be more dramatic things in some circumstances. So one topic that we've been interested in recently is how disks behave in binaries. Many stars, after all, are part of binary systems, and it may sometimes, or maybe often, be the case that the direction of rotation of the protoplanetary disk in those systems need not be aligned with the direction of rotation of the binary system. So here's a simulation. Here we have two stars, a protoplanetary disk surrounding one of those stars, where the disk is very strongly inclined to the orbital plane of the binary. And as you can maybe see from this movie, here the disk, the simulated disk, is ending up not at all axisymmetric, and flat, it's becoming actually quite eccentric as it evolves within this potential of the binary system. So if we're interested in disks in binaries, then clearly there can be quite large departures from axisymmetry, much larger than those small shears that we're talking about from these thermal effects, pressure-driven effects, in the last couple of slides. So those disks may certainly be eccentric. They may also be warped. They may not actually be planar. Are there small warps or small deviations from circular orbits in more typical disks? That, I think, is a question we don't really know the answer to very well. What's encouraging, though, is that observations are now sensitive enough to potentially probe those effects. So if there were small departures from flatness and from circular orbits, those are things we may hope to be able to detect by looking at the kinematics of gas within disks. Okay, so let's now go on and say something about temperature. And first of all, make a general comment about, is it a reasonable assumption to assume that stellar irradiation is the dominant thing that is heating the disk? So we have two possible sources of heating. One of them is the stellar irradiation of the disk. The other would be the liberation of gravitational potential energy as gas is actively flowing towards the disk and being accreted by the star. So that would be accretional heating, or sometimes I might describe it as viscous heating of the disk. So we can make a simple estimate here. Let's assume that the irradiational heating of the disk is some fraction f of the stellar luminosity, the fraction of the stellar luminosity that is actually absorbed geometrically by striking the disk surface. Now, the accretional heating overall is just going to be the loss of gravitational potential energy, so Gm star m dot, where m dot is the accretion rate of gas onto the star, divided by Rin, where Rin is some inner radius of the protoplanetary disk, which might be the stellar surface, or as we'll see later, it might be the magnetospheric radius if the star has a significant magnetic field. And generally, we'll get about half of that energy out in luminosity. As the gas flows in, the other half will go into increasing the kinetic energy of the gas around the star. So we can compare those two things and find that globally, this accretional term will dominate if the accretion rate is above some characteristic value. So if we have a luminosity divided by mass, there's just the solar value, an inner radius of 10 solar radii, and assume that the disk intercepts 25% of the stellar luminosity, that value is about 10 to the minus 7 solar masses per year. And the interesting thing for solar mass stars, at least, is that that kind of number is obviously not so different from the amount of gas that must flow through the disk in order to form a solar mass star in a few million years. So both heating sources, in principle, can matter. It will depend on the age of the disk. Presumably, disks will be accreting more actively at early times. It will also depend on where in the disk we are. And of course, it will also depend on the stellar mass. If we go to much lower mass stars, their stellar luminosity will be much smaller than the equivalent pre-main sequence solar mass star. So let's think a little bit about how that heating might work, focusing, first of all, just on the heating due to irradiation from the central star. And when we think about this, the physics here is quite interesting, and particularly if we're interested in the surface layers of the disk, can become quite complicated. So let's first of all think of the stellar photon. So here would be the star, would be somewhere off to the left, and here we would have the surface of the disk, which we imagine maybe has some flaring shape, so that it's sort of a bowl-like shape that is, has a direct line of sight down to the central star. So the young star will have a fairly red spectrum, so let's say that the stellar photons are something like micron wavelength. So these stellar photons will come in, and primarily they will immediately heat the dust in the disk. So unless we're very close to the star where the dust has all been destroyed, the dust will be the dominant opacity source in the disk, so it will be the main agent that will absorb the stellar radiation. So that dust will then be heated up by these stellar photons, and it will emit, and if the dust is near the surface of the disk, it may be able to emit directly back into space. So one component of the emission from the disk will be warm dust emission from this directly coming from these heated dust grains that are exposed to the stellar radiation. Now, those heated dust grains will also radiate downwards, or radiate isotropically, so they'll radiate half upwards and half downwards, and the radiation that goes downwards will go into the denser regions of the disk, be absorbed by more dust grains, and be thermalized within that region of the disk. So the second disk component will be optically thick disk emission, coming from this interior region of the disk. And generally, this will be at a somewhat cooler temperature than this warmer dust emission coming from the surface. Now, the dust will then interact with gas, and there'll be two main processes where that can take place. One is that gas molecules may directly collide with the dust particles and share their thermal energy as a result of those collisions. And then secondly, this dust may emit electrons by a process called the photoelectric effect, which will tend to heat directly the gas. So some of these photons, not these photons, but UV photons that have hit the dust, may be able to eject electrons, and those relatively high energy electrons will go into the gas, share their energy with the gas, and heat it in that way. And then that gas will cool. The gas may cool, of course, by colliding with dust particles, so it may be thermalized again by colliding with the dust, but it may also cool directly, and for example, it may cool by line emission, which we will observe from the surface of the disk. So these are the main processes, and in the next few slides, I'm going to go over some details of how this works. But I think now might be an appropriate point to take a break. So we'll take a break at this point.
Get a folder. So anyone who didn't get one of these, just raise your hands. Talk about what you've heard up till now, or the topics that Phil has talked about. Ask something that helps you engage with his lecture more. If you missed something, a term that you just didn't hear, anything that will help you continue on listening to lecture, get as much as you can out of the lecture. I'm going to give you 5 minutes. The room should get really loud, so I don't want to hear silence. All right, go ahead. the day to fill it out. If you want to remember what things you have asked to each other, you could write down, I think it's the third question on there. Just to remind yourself of the first thing you talked about today was.
Okay, so let's carry on, and let's first of all think about just the optically thick part of this emission. Okay, so what would be the simplest limit here? So there's only a small number of limits here that really can be solved exactly. Okay? And the one limit that can be solved exactly would be the case where you imagine that the disk is just an optically thick surface, a thin, razor-thin sheet in the equatorial plane of the star, which intercepts all of the stellar light which is coming in and hits the disk, and then it re-emits it locally as a black body. Okay? So here would be the setup. Here's the star. Here's this disk, now represented as a razor-thin sheet. We have some unit of area in the disk, and that surface area intercepts light coming at this angle theta from the disk. It reconverts it into black body emission and then re-radiates it locally. So in this limit, you can calculate quite easily what the flux of starlight coming down through this surface is. That would be the integral of the specific intensity of the star, which in a simple model we might just take to be a constant, some geometric factors here, and then d omega would be the element of solid angle. So it would be a fairly simple radiative transfer problem to work out then how much flux this disk receives. We just have to integrate over the surface area of the star that is visible from that point in the disk, taking note of the glancing angle with which those rays of light will strike the disk surface. So this problem is an analytic problem, so you can, in this limit, evaluate exactly what the disk temperature is compared to the stellar temperature, and it has this relatively straightforward analytic form. Now, what's important here is that if we're a long way away from the star, so r here is very large compared to the stellar radius, what you find here, expanding out this expression, say in a Taylor series, is that the disk temperature has a power law scaling with distance, and it goes as r to the minus 3/4. So if you then consider what the thickness of the disk would be, h over r, we said that that was the sound speed divided by the Keplerian velocity, and the sound speed will go as the square root of the temperature within the disk. So this square root of the temperature will be r to the minus 3/8. The Keplerian velocity is r to the minus 1/2. So the prediction here from this very simple model would be that h over r scales as r to the 1/8 power. So the thickness of the disk, measured, if you like, by the opening angle it makes as seen by the star, will increase as we move further away. In other words, we would say that the disk usually flares as we go to large radius. Okay, so that's the simplest model. There's additional physics that has to be considered here if you want to make a more realistic model. Part of that is simply that if the disk flares, of course, it's not then an infinitely thin, flat sheet. It's actually, if you like, rearing up as we go away from the star. And so the outer parts will intercept more stellar photons than they would if the disk was completely flat. That will in turn tend to increase the tendency of the disk to flare, because we'll be heating the outer part more strongly than the inner part. Then the second part is something I already alluded to, the surface dust, the dust that is directly exposed to the stellar radiation, radiates somewhat inefficiently, because typically the dust particles that we're interested in are small compared to the wavelength of the light that they will be re-emitting. So rather than being, if you like, an infinite surface, we really have to consider the finite size of the dust particles and the fact that they're small compared to the wavelength. So if we consider the thermal equilibrium for dust of some particular radius, the absorption would just be the flux from the star times the surface area of the dust particle that is seeing the stellar irradiation. And then when it re-radiates, we'll have sigma t to the fourth, so this would be the Stefan-Boltzmann constant, this would be the black body emission multiplied by the surface area, but then there will be an emissivity term
which reflects this inefficient radiation of very small dust particles.
And typically that emissivity will go as something like the temperature to some power beta, where beta is of order
unity.
Now, if we just solve this thermal balance equation, you get a prediction for what the temperature of this warm surface layer of dust would be, and it's just what it would be if it was
Directly exposed to starlight and re-radiating as a perfect black
body, but then there's a correction term, which is this epsilon to the 1/4, and if epsilon is smaller than 1, this implies that
the surface temperature is larger than what it would be if it was just an efficient radiator. So the prediction for the dust emission is that that surface layer of dust, the dust will be superheated above what you would be sort of the naive temperature you'd expect, say, if you were doing a planetary atmosphere equilibrium calculation, and you'll be getting out an optically thin emission component that it's at a warmer temperature than you would expect. Okay, so these things can be looked at to some extent in analytic models. Quite a popular one was developed by Chang and Goldreich now many, many years ago for some fairly reasonable, this should be r to the minus 3/2 there, so for a minimum mass solar nebula density profile around a half solar mass star with particular temperature and radii. And for that particular model, they derived expressions for the interior temperature, so that would be the temperature of the black body emission that is coming really from the central part of the disk, and from this warm surface layer of hot dust on the surface. And in this simple model, half of the emission comes from that black body at the interior. The other half is radiation that is directly re-emitted by the warm dust particles near the surface. And these kind of models have been improved later. This is work by Pascal Gerard and Doug Lin, now almost a decade ago still. They had a version which included also accretional heating as well as stellar irradiation, still sticking to an analytic prescription for what the temperature should be. Now, the general results, I think, that you should know here are that if we have passive disks, so disks mainly heated by stellar irradiation, the rough profile we expect to get is that the temperature goes as something like r to the minus 1/2. So it's a little bit flatter than the expression we would get if we just had that razor-thin disk that was really completely analytic. It's also flatter, as we will see, than the profile you'll get from accretional heating if the dominant source is loss of gravitational potential energy as gas comes in towards the star. So we predict then that disks should flare to large radius and that the accretional heating, relative to the stellar heating, will typically be larger close to the star than far away. So if we're interested in, say, where the snow line is, pretty close to the star, that can be very strongly affected by accretion. If instead we're thinking at 50 or 100 AU, starlight, stellar irradiation is very likely to be the dominant source of heating. Now, what about the gas temperature? Well, the gas temperature is somewhat more complicated. If the density is very high, then we can just say that there will be frequent collisions between dust and gas molecules, and that those will bring the two species to the same temperature. So if we're interested in the dense midplane of the disk, that equilibration process will be rather efficient, and we'll just end up with a situation where the gas temperature and the dust temperature are the same. On the other hand, if we're much lower densities, first of all, this process of collisional relaxation, if you like, between the dust and the gas may be quite inefficient. And then, moreover, we can also have a fairly strong component from this photoelectric heating process directly coming from dust particles. So what's going on here is that you have a dust particle which is now exposed not just to infrared radiation, but also ultraviolet radiation. So let's imagine, say, you have a 10 electron volt photon coming in and striking this dust particle. Well, most of the time, that energy will just be absorbed by the dust particle and go into heating it up. So that would be just the same as if the particle was being heated by infrared radiation. But some fraction of the time, maybe of order 10% of the time, instead we'll eject an electron into the gas, and the energy of that electron will be the energy of this incoming photon minus the work function of this surface, how much energy it takes to actually eject that electron and move it to infinity. And typically that might be, say, 5 electron volts, depending on what the dust particle is made of. So what you can have here is actually quite an efficient way of heating the gas. 10% of the time, half of the incoming energy goes directly into gas heating. So if you like, 5% of the incident UV flux goes into heating the gas directly. Now, when that gas is heated, it will then cool, and it can cool, for example, through rotational transitions, say of carbon monoxide. can also cool through atomic fine structure lines of the kind that are often considered when you think about the interstellar medium of galaxies. So here are some models of this. This is a review by Henning and Semenov from some earlier work. This is plots of dust temperature, gas temperature, and gas density in hydrostatic equilibrium. This is radius, and this is height. And the sort of general structure you get here is sort of a combination of the pieces of physics that we've already talked about. We have an optically thin, vertically isothermal structure near the disk midplane. We have warmer dust near the surface. So here you can see the surface temperature of the dust, this green color, is higher than these blue colors, which are being obtained near the disk midplane. And then the gas temperature is generally warmer still in these surface layers. So even though the midplane of the disk is generally very cold, if instead you're interested in gas emission that is coming from the surface, here you can see you have actually quite high temperatures, 1,000 Kelvin here, and we're looking at scales between 10 and 100 AU away from the star. So depending on the tracer we're interested in, whether we're interested in the optically thick dust emission, or instead are interested in various gas tracers which are coming from the surface, we can really be probing temperatures that are orders of magnitude different because of the height dependence of the temperature. And these kind of calculations really need numerical codes to compute, and there's a variety of codes, including public domain codes, which you can use to make these kind of calculations of the gas and dust temperatures. Okay, so let me now finish up by saying something about ionization, which is the other aspect of disk structure that's important. So the ionization fraction we define as the electron number density divided by the number density of hydrogen atoms. And this is really rather critical for both chemistry and also for how well the gas couples to magnetic fields, which when we talk about turbulence tomorrow will be a central part of the discussion. So if we first think about thermal ionization, well, the gas will, if you like, become fully ionized when hydrogen is ionized, and characteristically that occurs at a temperature of about 10,000 degrees Kelvin. Now, this is a temperature that is not normally reached in protoplanetary disks, right? This is hotter than the surface temperature of the stars that the disks are surrounding, so you don't normally reach 10,000 Kelvin in the disks. But it turns out that when we think about very high accretion rate states that are attained during outbursts, you can reach those temperatures near the midplane. And this turns out to be important because when you ionize hydrogen, the opacity, this is the opacity as a function of temperature, the opacity changes very dramatically over a relatively small range of temperatures. So that change in opacity with temperature turns out to be very important for models of outbursting behavior in young stars, and we'll come back to that in more detail. Now, another thermal ionization part that matters is the alkali metals, which are the species that are ionized most easily within disks. And the ionization of the alkali metals occurs instead at a temperature of about 1,000 degrees Kelvin. So those are temperatures that are still only reached in the inner parts of disks, but nonetheless they are in the inner regions before we get directly close to the stellar surface. So here's our plot of the ionization fraction as a function of temperature, taking account of this alkali metal ionization. And you can see that these numbers here for the ionization fraction are rather small. So even when the alkali metals are ionized at about 1,000 Kelvin, you get an electron fraction of about 10 to the minus 12. Now that's a very small ionization fraction, but again, as we'll see tomorrow, that turns out to be about the magnitude of ionization fraction you need to couple magnetic fields efficiently to the gas. So the alkali metals, sodium, potassium, and so forth, their ionization state can make potentially a large difference to how the disk responds to magnetic fields occurring within the innermost AU from the star. So this kind of calculation is relatively simple. Many of you will have seen this can be done using the Saas-Fee equation, and the answer you get is just a function of the temperature and density within the disk. So we'll say a little bit more about this, about non-thermal ionization, but I think we'll defer that now to the second lecture in the afternoon, and we will stop there.
Fine motor skills, turn this sheet into 4 little pieces of paper. however you would like to do it. And it will be anonymous. Again, all of this is anonymous. It doesn't matter who you are. It just matters that you get a chance to ask the questions. This will also help Bill understand how you saw his lecture, because you're coming from such a wide variety of backgrounds. So that first one, again, the question is, what are you still confused about, or you didn't understand, or still somewhat unclear at the end, by the end of his lecture? And as you're filling those out, when you're done, send them to the ends of the aisles, and I'll pick them up. And while you're doing that, I think questions can start.
Yeah, so the question was, what are the uncertainties in calculating the density profile and so forth? I would say if we're interested in the literally just the density profile and the velocity profile, then the main uncertainties would come from the assumption that the disk is really axisymmetric. So if the disk is axisymmetric, then the terms that are being neglected there, the viscosity, the magnetic fields, and so forth, probably are being justifiably neglected. So in that sense, the calculation is quite precise and accurate. However, of course, the disk might not be completely axisymmetric, and then the velocity field, say, would be different. When we come instead to think about the temperature, then differences in the opacity due to having the dust perhaps having grown into larger sizes and things like that, those would certainly be expected to vary at different points in the disk. And it's not so easy to really quantify how much uncertainty is introduced by that kind of situation.
Just curious, the prototype disk models that you see, do you just see inner edge extend all the way to central orbit, or
So in some of the things I've been just saying here, we're effectively assuming it went all the way to the star. So we'll discuss in this afternoon. Generally, the only circumstance where you really expect the disk to extend all the way to the star is if the accretion rate is very high. Typically, it will be truncated by a magnetosphere, and that might be at 10 stellar radii or some number like that. And that will make a difference to how the disk evolves, and a lot of observational signatures. It shouldn't make so much difference to anything we've talked about this morning.
so far the heating is concerned due to stellar radiation, is that going to be that we observe a disk where the edge extends all the way to the star?
Yeah, so the question of where the edge is will be very important from an observational point of view, perhaps particularly if the star is a little bit more luminous than a solar mass star. Then actually the direct heating of the inner edge of the disk could be quite significant. And for example, the inner edge might puff up and start shadowing the outer part of the disk. So even though in general we expect the disk to flare, there might be circumstances where there's sort of at least in the inner part, there's enough perturbation to that structure due to where the disk is truncated, yes.
Temperature gradient you showed, so are they typically less than the gradient which we can start a convection in the disk, or?
Yeah, so the question was, are the temperature gradients going to be convectively stable? So there's sort of two parts to that story. So the simple part is in the vertical direction. And so in the vertical direction, certainly, of course, if the disk is irradiated, then it's isothermal, and that will be convectively stable. If it's instead heated near the midplane, whether it's convectively stable will depend a lot on what the opacity is. And it might be stable or it might not be. There's then, however, a second question, which would be, would it be effectively convectively stable in the radial direction? And there, generally, the effect of rotation will be to stabilize you against linear convection. So you don't expect in the radial direction there to be really sort of standard convection, as we will say a very little bit about. There may be, if you like, analogous process, entropy-driven processes that are not quite convection, but which could take place in the radial direction, which are non-linear processes. So there could be a role for entropy potentially in both directions, yes.